So yesterday, we talked about the top half of this project that we were working on. So we talked about assembly importing, scanning in Geomagic, and mesh manipulation. And today we're going to talk about some mechanism design, digital fabrication and manufacturing, and then some 3D printing export options. But just in case you weren't here yesterday, I'm going to do a quick little summary of the scope of the project that I'm talking about here, so you're not out of the loop too bad. So for this presentation, we're going to be working with the Luan-Sol arm. It's a simple robotic arm that fits within our budget that I was allowed to play around with. So it uses multiple servos and it's controlled using a cell phone or a Bluetooth controller. So we chose to work with it because it could challenge all levels of our business expertise. So from solid modeling to 3D scanning, all the way to 3D printing. So in our brainstorming session, I chirped one of my colleagues and I told him that I could use this arm to model in SolidWorks better than he could. And with that, our night school concept was born. So what we decided to do is we decided to create a gripper. So this arm can manipulate a mouse, and then I could kind of put my money where my mouth is. So we started the project off in our scanning department, and we used the RTX scanner to scan the mouse as well as a hand, because no one really wants to model a hand using the surface modeling tools. That is just no fun at all. So then we took all of the scan data and an IGIS assembly, and we put it all into SolidWorks. And we did some preparation for the models. We ensured fitment, function, everything like that. And that's kind of where we left off yesterday. Today, we're going to talk about exporting options to our 3D printers and then some design requirements that 3D printers require. And then for this build, we chose to use the HP MultiJet Fusion printer. And that's because of its near isentropic material properties, clean surfaces, and very fast print time. So near the beginning of the design, we weren't really sure what we were going to do. So we made a couple prototypes to change the mechanism here. So what I'm going to talk about is the servo on the gripper wasn't ideal for picking up kind of heavy objects and things like that. So we wanted to replace it with a pneumatic cylinder that was a little bit more powerful. And during that design process, I'm going to talk to you about how we used sketch blocks and the assembly layout sketch environment and motion studies to validate our design and design it really quickly, all in 2D, before having to make any three-dimensional models. So we started out with this original assembly, which is driven by an electric servo motor. And we wanted to modify this design to use a pneumatic cylinder. So what we're going to do is we're going to start by simplifying the existing linkages by converting it to 2D geometry. And the Convert Entities tool is perfect to grab the outline of this geometry and take it from 3D into 2D. So after each of those linkages is converted, I'm going to turn them into blocks so we can manipulate them like individual components at the sketch level. So you can do that by just selecting the entities and then using the shortcut menu to create a block out of them. So we're going to move this to its own assembly, but I want to ensure that we maintain the correct spacing between the pivot points. So a quick measure between the center of each of these cylinders will give us the dimensions that we need. Control selecting the blocks and using Control C to copy them will let me later paste them into a new assembly. Once we create a new assembly, we're going to start a layout sketch and paste the blocks we've copied from the original assembly, which we'll use as a starting point. So a layout sketch in an assembly is used to test 2D linear motion without having to do any three-dimensional modeling or create any part files. It's all just sketches. So using those previously recorded measurements, I'm going to use construction geometry and dimensions to establish the appropriate distance between these pivoting holes. So to create the same motion, we need to add some relations between each of the sketch blocks in the same manner that you'd use mates in an assembly. So first, I'm going to concentrically relate this link to the origin. And for all these pin connections, a coincident relation will act like a concentric mate, allowing rotation, but no translation. So now we can easily drag around the linkages and understand the mechanical system in a 2D environment. We can use this to make informed design decisions before having to do any 3D modeling. So one benefit of layout designs is being able to simply edit each one of these sketch blocks individually and see how the motion changes. For the new design, I'd like to use a 25mm stroke cylinder. So laying this out is as easy as creating a few dimensioned sketch entities. And I lost my positional relation to the origin, so adding that back will result in a new motion pathway for this mechanism. All just by changing the sketch. Haven't made a single part yet. This is all in 2D. So another benefit of these layout sketches and assemblies is being able to run an actual motion simulation to get early insight on the mechanism. So we're going to come in here and add an 85-degree rotation to the mechanism. And I'm just going to pull the simulation time down a bit to 2 seconds here, and then run this simulation. And I can see exactly what happens. With SolidWorks Motion, we're able to extract all kinds of values related to the force, torque, relative displacement, and much more. Here, we'll trace a path of the motion to understand exactly where the gripper will be throughout the entire motion of the mechanism. This could also be very useful in certain CAM design applications. And I can go through any step of the simulation and see exactly where that point follows along my path. So going through the natural evolution of a design, once we get the mechanism refined enough in a 2D environment, we can move to the 3D. So layout sketches make this easy by giving us the ability to derive a part from each of the blocks in the layout sketch. So now that sketch is inserted into a new part, and I can make another sketch over top of this with some simple features that are going to reference that block. So I have those key points that I need to maintain. And I can dimension my holes here and slap on a slot. And now I have a feature that can really bring this part to life. Just a nice simple extrusion. And it is related to that original block sketch. So if I do make any changes, that part will automatically update as well. So coming in there, putting in my pneumatic cylinder. Right now, this block is saved as a virtual part. So like I talked about in the previous webinar, but we can see that we can change that to an external part because we actually need to print this out. We don't want it to just live inside of the assembly. It is now its own part that I can save as an STL and throw out to my printer to get made. So it has some references right now, and I want this part to not have any of those external references, so I can break those references if I want, but then I lose that associativity. So it's kind of a balancing act between what you would like to do. So we didn't end up going with that design because, as you saw, we decided to scan a hand instead and use the mouse. So I'm going to move into the next section now. So most people like to imagine that 3D printing has no design limitations and anything can be printed. But like any manufacturing process, there's criteria that have to be met and scenarios that should be avoided to get the best results for your product. In this section, I'm going to talk about the printers that we work with here at Hawkridge Systems and touch on a few of the design considerations unique to those printing processes. So we work with two brands of printers here, the Markforged and the HP. Those machines use different printing processes, so the processes talked about in one area are not relevant to the other. So for the Markforged machine, I'm going to touch on optimizing hole patterns, orienting your part print for accuracy, orienting your part for strength, and then some secondary operations you can do on your prints. So right here on your screen, this is a list of 3D printing technologies. Markforged uses a process called fused deposition modeling or fused filament fabrication, and it takes thermoplastics like nylon, ABS, or PLA, and it squirts them out of a nozzle, lays them down on a plane, and then that is your print bed. So it kind of reminds me of squeezing toothpaste out of a tube, but at the micrometer scale. So these progressive layers are then added up to build the part from the ground up. So this is a graphic of a Markforged machine and the first part that we're going to talk about. To understand the orientation, let's look at the shadow of the part on the right-hand side there. So right here, this shadow, this is our kind of top plane, that's going to be our print bed. And to understand how our orientation is going to affect us, let's look at some of these holes. So the holes on the part here are perpendicular to the print bed. And because of that, some issues could potentially occur. So this is an exaggerated layer thickness, so we can actually see the layers. Clearly, the machine has a way better resolution than this, but I've exaggerated the layer thickness to prove my point here. So because of this orientation, the layers near the top of the hole, they bridge a large gap, or they start cantilevering over the edge. So right where my blue arrow is pointing, there's one layer that goes all the way across the top, and then a few that are kind of cantilevering over. So depending on the geometry, the upper layers could sag and droop. And then that's going to require support material to hold them up. So adding support material in your prints increases the time and cost of the print. And that's because more material is used, and then it has to be removed after the print. So what you can do to avoid that is use some different shapes. So if your product does not need the hole to be perfectly round, there's a few geometries that are self-supporting. This diamond shape can still fit a cylinder through it, but requires no supports during printing. So that's going to reduce your print time and your material usage. So a nice rule of thumb when using the Markforged printers is that a 45-degree angle or steeper won't need supports, but of course that depends on the length of the cantilever and how much weight is above the print. So luckily the software will calculate where you need supports for you, but of course you can customize that if need be. Another possible geometry is this teardrop bore. So this gives you some more options because the bottom's still round if that's required by your design, but the top tapers off at that 45-degree angle, which will require no supports during printing. So that's going to give you a smaller printing cost because there's less material used, and then no post-processing afterwards. You don't have to snap all those off and smooth off any surfaces. So when I created a print job for this part in the Markforged cloud-based software Eiger, I got these time, material, and cost estimates. The circular hole cost about $10 more and took 3 hours longer to print than the other two. So that's a pretty big difference considering there's only 3 holes in this design. So just by changing the geometry there, you can save material, cost, and most importantly, time. Another design consideration when using the Markforged is orienting your parts on the print bed for accuracy of the features. Looking at this top graphic, the circle is oriented on the plane of the print bed, letting the nozzle create the feature as one continuous tool path. This is ideal for the accuracy of the shape, as it will be one path and not a bunch of discrete little lines creating a circle. The graphic at the bottom is oriented perpendicular to the print bed, just like we saw in that previous example. So this is going to result in less accurate curvature of the circle because it's made up of a bunch of multiple disjointed lines. So when you're using the filament fusion process for 3D printing, you have to consider the orientation of your part on the print bed, and sometimes you have to make sacrifices to certain features. So if I have holes going in both of those directions, I need to make a choice on which ones I'd like to be more accurate, depending on if they're weight bearing or not, and a bunch of different factors that we're going to talk about a little later. However, there is an option to do secondary operations on these Markforged parts. You can drill them, you can tap them, you can do PEM inserts or press fits. And these post-print operations can take some of that orientation pain out of the process. So some feature accuracy does not need to be sacrificed. So you can always drill in a new hole in that perpendicular to the print bed direction, or press fit a bushing in there and you know that bushing is perfectly rounded or rounded enough for your needs. So you don't have to design every single feature inside of your model before printing, because you can do some post operations on these materials as well. Another consideration for the fused filament fabrication process is orienting the part for strength. Before I send a part to print, I ask myself a few important questions. If the part is load bearing, what direction are these forces coming from, and what type of forces are they? Are there fillets and chamfers, and how important is the accuracy of their shape? What are the critical features of the part in terms of strength and accuracy? And do some of those features need to be printed, or can they be replaced with easily accessible components or secondary operations? So the answers to these questions, of course, comes with experience. And there's no better way to learn than to do it wrong and make mistakes. So let's talk about orientation for strength. So since each layer adheres to adjacent layers, parts are always stronger in the plane of the print bed. So aligning the loads with the plane of the print bed will utilize the ideal material properties. So again, remember this graphic has over-exaggerated layer thicknesses, and those loads will be distributed across multiple layers. The way that it looks right now is that those individual layers might shear with each other. But of course, think of those 3 arrows as one distributed force, and then that will make a bit more sense. So loading in the direction normal to the print bed stresses the bonds between those layers, and you should always try and avoid that if you can. If your part has very complex loading and it's getting loaded in all directions, and clearly you can't avoid it, but the worst culprits or the highest stresses, highest loading should always be in the direction of the print bed, not normal to it. So to utilize the information on the last slide, we're going to talk about a little case study. So these two brackets are printed with identical print settings, and we're going to be testing them for strength. The only difference is going to be their orientation on the print bed. So we can see that grid system there, that's the print bed. And we're going to call the one on the right horizontal and the one on the left vertical. So the prints are going to be loaded like you see in this picture. And you can see how happy my colleague is to be holding up his own body weight with one hand. He is very proud of himself. But using these two images, we can understand exactly how this is going to be loaded. So with that loading in mind, which orientation do you think is going to fail first? I'm going to let you examine this slide for a moment, and then I'm going to put up a poll to see who's actually been paying attention. Very good, everyone. So the majority of us said that A will be the one failing first. So as we can see, the vertical orientation failed first, and that's because the loading was normal to the plane of the print bed. So this did not utilize the ideal material properties. So option A failed at about 30 pounds of force, and option B maxed out my tiny little scale there. So just by orienting the part differently on the print bed, we more than doubled the strength of the part. So some forethought before you start your prints is really ideal. So the other side of the coin is, which orientation do you think is going to print faster? So the horizontal orientation will print faster, and that's because option A is going to need supports, and because it sits higher off the print bed, it needs more layers to print. So both of those are deciding factors in the print time. And looking at the print time, it's about 5 hours for option A and only 2 hours for option B. And then the difference in material cost, of course, is the support material. So many people think that being able to print assemblies as one part is the best thing about 3D printing. But sometimes that's not your best option. This design right here passed across my desk, and I got the SolidWorks model as one part. So before I jumped into printing, I asked the designer what the important features were. And I was told that the flat faces of the plates need to be as accurate and flat as possible so that there is a good seal with what it's connecting to. So in order to ensure a flat surface, I chose to break the model up into pieces and assemble it after the print. Because you can see the way that it sits, that top face would be at an angle, and it would have some layer striations in it or layer lines in it, and it wouldn't be perfectly flat. So the best way to get that flat face is to put it directly on the print bed. So that's what I did for those faces. And I could also orient the tubes in a way that the circular features are oriented the best that I possibly could for accuracy and strength. So luckily for me, SolidWorks has some great tools to make that process really easy and nice and simple. So the tools that I use within SolidWorks is the split command. And the split command breaks up an existing part into multiple bodies or an assembly with no material removal. It just separates the bodies. So this is great for imported features or splitting a model into portions. So what made my job even easier was that the part was created in SolidWorks. So each feature has the merge results option. So all I had to do was clear a couple checkboxes, and then I had a multi-body part at my disposal. The Markforged software Eiger has an automatic infill pattern. And you can use that to take a completely solid part and strategically hollow it out. You can do a rectangular fill, a hexagonal fill, kind of like that honeycomb shape, or a triangular fill. And it's as easy as just selecting from a pull-down menu. So you can make your parts still structurally strong, but significantly lighter, which will save you in material and print time and all of that fun stuff. So now we're going to talk about the HP machine and some design criteria you have to meet in order to print successfully. We're going to talk about assembly spacing, deboss and emboss minimums, and optimizing the weight of your part. So this is the HP MultiJet Fusion in all its glory. I really recommend you guys stopping by one of our digital manufacturing labs to see this thing in action. It is really cool. The HP machine uses a powder bed fusion process, which can also be called SLS or MJF, or MultiJet Fusion. So right now, we're looking at the printing process in the HP machine. So a thin layer of powder is distributed across the print bed. Two nozzles then move across the print bed, distributing a fusing agent and detailing agent, both of which change the melting point of the powder. The fusing agent controls where the nylon powder should be solidified, and the detailing agent surrounds the boundaries of the part to create fine details and surface finishes. This process is repeated layer by layer, and fusion happens inside the machine, causing the part to be nearly isentropic. Because the material is isentropic, and if you don't know what that means the material properties are identical in all directions. So because the material is isentropic, you do not need to worry about optimizing for orientation or strength, and you can then focus on getting as many parts into the print bed as you can and start optimizing for time and cost. So when we're talking about 3D printed assemblies, there's two types. There's a manual assembly and then the printed assembly. So with a manual assembly, the parts are printed individually and assembled after the print. So just like any standard manufacturing process, you make one part, you make another part, boom, they fit together with whatever fitment method you designed. But with a printed assembly, the two parts are assembled in the STL file or SolidWorks file, and then they are printed as one assembly. So they don't come apart, they're not assembled afterwards, they are printed fully functional as one piece. So in this example, we're going to talk about a printed assembly. So you can see I have the green piece and the transparent piece, and there is some motion in there. There's that nice little ball joint, but they are going to be printed as one part. So I'm not going to assemble it afterwards. So a minimum clearance of 0.5 millimeters or half a millimeter is required to ensure that the parts do not fuse together. You also have to make sure that there's a way to evacuate the unfused powder from the vacant space. So if you have an area completely enclosed in fused material, there's going to be powder trapped in there. So you need evacuation ports, holes, slots, slits. So then you can either use a vacuum or air gun to get any of that air out. For thicker parts with a wall thickness of over 5 centimeters, a higher gap is recommended because the heat stored within the thick walls might bleed out a bit during the cooling process. So once you get within that 5 centimeter range, you might want to do a couple test parts to figure out what gap works best for your geometry and tolerancing. So manual assembly, so something like this little gold claw at the top and the threads into the green piece are of course printed as individual parts and then assembled after the print. So parts of an assembly that are printed separately, you can have a gap tolerance of 0.4 millimeters. And in the print bed, those parts must be 2 millimeters apart from each other And of course, that is kind of geometry dependent, but that's a great rule of thumb so you don't run into any trouble. When you are embossing or debossing features, like my nice branding I put on this thing, you want to have at least a 1 millimeter depth of your text there. So that extrusion is 1 millimeter up and that cut is 1 millimeter deep. And that's a minimum. Of course, you can go deeper or taller, but that's a minimum you need so it's actually legible. You usually want to orient those in the XY plane for printing, especially if they're really small. And you want to make it facing up on the print bed. So you don't want those pointing down, you want those pointing up and oriented in the XY plane. So that is really the only orientation limitation that you would need to focus on with this HP printer. So with all of those rules, SolidWorks has some awesome tools to help you in that regard. The first one being the clearance verification tool. So what that's going to do is that's going to check clearances between components or faces within an assembly or multi-body part file. You can do that to validate your design tolerances, and it's all in one tool. So for our hand, the little cam that's in there, we use the clearance verification to ensure that it can slide in afterwards and be mobile. So we didn't print that as one assembly. They were separate and we assembled it afterwards. If your design does not meet those specific criteria, there are also tools within SolidWorks to help. So the Indent tool will create an offset pocket on a target body using an existing tool body and clearance value. So in this graphic here, my tool body is my cam, my target body was the hand, and I can use the Indent tool to remove material to ensure I have the appropriate clearance. Now the preview I have there is jacked up to way too big of a clearance, but I just did it so we can see exactly what's happening. So unlike Markforged, which has that infill options, the HP printer does not have that automatic infill. But luckily, if you're a SolidWorks simulation professional user, you will have access to Topology Optimization. And what this topology study will do is you can put in your boundary conditions, so your fixtures, loads, maybe a manufacturing process for symmetry, things like that. And you can let SolidWorks remove material to maintain your structural integrity. So you can optimize for mass while still maintaining a factor of safety or minimum stress value to help kind of optimize your designs and give you really organic looking shapes, which are ideal for 3D printing. Kind of like this hood hinge assembly right here. It used to be a solid brick. And then Topology Optimization found this really unique internal webbing structure to meet all of the design specifications and greatly reduce the mass of the thing. So if you have more interest in that, we have a bunch of content on our YouTube channel. Reach out to any Hawkridge employee and they can get you tons of more info on Topology Optimization. And finally, once we made our mouse ready for digital fabrication, we had to export it to communicate with our 3D printer. So what file types should we be exporting in? STL, 3MF, are there others? Which is the best? What are the options? Those are kind of the questions that I'm going to try and answer today. So the STL format was developed in 1987 by 3D Systems for SLA 3D printers and has mostly remained unchanged because it's simple, reliable, and widely supported by virtually all 3D software packages in the engineering, design, and additive manufacturing industries. So what it does is it uses linked triangles described by XYZ coordinate points to recreate the surface geometry of a solid model. So because it's all described by those coordinate points, it is a nice interface between all the different CAD kernels and systems like that. So there are two parameters that control an STL file that determine how accurately it represents the solid it was created from. The first one is the deviation or chord height, and that is the maximum distance that SolidWorks will allow between the surface of the original 3D model and the surface of the STL file. Using a smaller deviation will help represent more accurately the curvature of a surface. The recommended value for the deviation is about 1/20th of the 3D printing layer thickness and never below the resolution of your printer. Exporting in a smaller tolerance will not have any effect in the quality of your print. The angular tolerance limits the angle between a tangent surface and the adjacent triangles. The default setting is 10 degrees when you pull your slider all the way to fine in SolidWorks. So if a high quality curved surface is needed, then you can pull that setting down all the way to 1 degree, which is recommended for the highest accuracy of very curved surfaces. So faceting is a consequence of STL files. And settings for angular tolerance will determine how round and smooth the STL will be, which is a really large factor in print quality. So even the fine setting in SolidWorks can produce a definite faceting in prints. So our recommendation again for prints with desired high quality surfaces is 1 degree. So if you look at the jar on the left of the screen, you can see these vertical lines that are caused by the large faces meeting each other. The jar on the right does not have those vertical lines because the angular tolerance was pulled all the way down to 1. So right on the left, there's that core setting, and you can see the faceting and those lines, and then on the right, it is significantly smoother. So a common issue is the file size of an STL, and you have to use your judgment to balance the file size with the quality of the export. So file sizes can be extremely large if mesh is significantly dense, and this is really common with curved geometry. So you can see in there where it's curved, you can increase the density of it and the file size will jump up significantly. So increasing the resolution above a certain point really brings no additional benefit. But unfortunately, that is all geometry dependent. There's no magic number. You just, oh yeah, always export this exact settings and it'll work out. There's some guidelines that you can tweak, but it is all geometry dependent. So I decided to go as crazy as I could with my mouse scan, and I maxed all the settings and I made about a 0.5 gigabyte file here. So I definitely not recommend this because it took me forever to save it, and I have not yet had the patience to try and open it in SolidWorks. That would just take far too long. So remember that choosing the correct unit system is as important during export as it is during the import. And then of course, communicating those units to whoever you're collaborating with or working with, so then they don't have to guess and check or make the wrong assumptions. So the options when you are exporting to an STL file are listed here on the screen. The first option you have is your output as. So a binary file is smaller. It's about 5 times smaller than the ASCII, but unfortunately it's not as supported. So the ASCII is supported by most systems. The binary depends on the system, but it is usually smaller. The next, you have those resolution settings where you can tweak your deviation and your angle. And we talked about those in the previous slide. Then you have your show STL info before saving the file. So that's really nice because it will give you a preview during the export process there. And then you can see if you like it or not and stop it if things start to go awry. You can turn on check for interferences and save all components of an assembly into a single file as well. So that's really nice because if you have interfering geometry, you're going to have a bad time when you try and either print it or import it into something else. So there's a different file type called the 3MF. So several industry-leading companies were brought together by Microsoft in 2015 to develop a format that addressed the limitations in not only the STL format, but also other popular but aging 3D formats such as OBJ and VRML. So it was originally created as a standardized framework for Microsoft hardware and software ecosystems to allow users to simply hit the print button, just like they would in any other documents, and reduce the complexity of the print process. The 3MF file type was released after initial development in an open format to help with adoption, as well as innovation as new hardware and techniques are developed throughout the industry. So the 3MF file type stores a much wider array of information than the STL does. So it can include things like color, textures, metadata, and of course the unit system. As far as functionality, the 3MF file also holds information that a printer would need, such as support structures, all while being significantly smaller in file size. It can even save information such as how assembly components will be arranged on the build tray, or how to print multiples of the same part at once. So this is a nice comparison of the 3MF to those other three standard file types. And you can see 3MF is the only one that can do all of them. Texture support, full color, units, built-in support structures, everything like that, all in one file set while being a smaller file size than the STL. So for comparison, we have this nice little bar graph right here. So an STL file that's 15.6 megabytes went down to 3.3 megabytes. So that mouse file that I did, that was about half a gig, I saved that as a 3MF and it was only 13 megabytes. So that is a significant drop in file size while maintaining that same quality. However, it did take me about the same amount of time to save it. So it did compile it better and more efficiently, but it still took quite a while to save. So you can see here the software that supports the 3MF. So of course, SolidWorks is in there, Dassault Systems, our HP printers, pretty much every major CAD software will be able to output to this, as well as your major 3D printing brands as well. So for a full list of printers and machines that support it, you can go to that little 3MF website and have fun scrolling through the giant list. The options are really similar to STL's, but they include things like save color and materials. And since Dassault and HP have announced alignment of their future technology roadmaps, additional options are on the way, specific to HP printers. So again, that preview file before saving option is really nice because it'll give you an estimated file size and number of triangles while you're still in this export window. So you don't have to just sit there and wait and be like, oh, it's too big, or oh, it's still too small. It'll give you that info right there. So the preview before saving with the triangles and the file size, super handy, very convenient. There's another file type as well, and it is called the AMF, or the Additive Manufacturing file, AMF. So it is really similar. It can do pretty much the same things that the 3MF does. The only difference is that it wasn't adapted by as many companies. So it exists, but no one really uses it, but it is there as an option. So on a side note, since exporting does eat up a lot of time, there's a tool inside of SolidWorks called the Task Scheduler. So anyone with SolidWorks Professional has access to the SolidWorks Task Scheduler, which can export out files in a batch operation. Or you can schedule them during downtime or off hours, so your licenses and designers are not being tied up just watching that export bar or a green bar go across the screen. There's nothing worse than that. So you can have it during non-business hours exporting these, or during a lunch hour. You can have them scheduled for whenever you need them to. And with that, that is the tail end of our presentation. So this is the final version that we ended up making. I did end up losing my bet. I could not model better using this robot and a PS3 controller. I did not have the control that I hoped I had. And thanks again for watching, humoring me, listening to me. I enjoy doing this, so without an audience, I can't do it. So thanks for signing up, and I wish you guys the best of luck in all of your future endeavors.